Hi, I'm Dongyan Lee. Let me introduce our works today. Fix the noise, disentangling source feature for controllable domain translation. Given a source model, our method can smoothly control the degree of source domain features in a fine-tuned model. Our approach explicitly guides the model to preserve the source features by using the anchor point, which allows a flexible and smooth cross-domain control. Recent studies show strong generative performance in domain translation, especially by using transfer learning techniques on the unconditional generator. However, the control between different domain features using a single model is still challenging. Existing methods often require additional models, which is computationally demanding and leads to unsatisfactory visual quality. In addition, they have restricted control steps, which prevents a smooth transition. To control features across domains in a single model, we argue that the source features should be preserved but disentangled with the target in the model's inherited space. To this end, we focus on the fact that the noise input of style GAN2, which is added after each convolution, expands the functional space composed of the latent code expression. In other words, the feature space could be seen as a set of subspaces corresponding to each random noise. Remark that style GAN2 contains two types of feature spaces: an intermediate feature space that consists of feature convolution layer outputs, and an RGB space that consists of RGB outputs from tRGB layers. We choose to preserve the intermediate feature space H for the following reasons. First, it has recently been found that the feature convolution layers change during transfer learning, which indicates that source features mostly vanish in H second. Matching features of the source and target models in H enables the subsequent tRGB layers to learn the target distribution. Consequently, preserving H space enables the model to maintain coarse features of the source while learning fine features of the target. From the same latent code, we encourage the target model to have similar features as those of the source model in H using a simple feature matching loss as shown in the figure. Constraints on H go beyond simple color filtering effects applied on source images, which is shown in other spaces. The feature matching loss enforces the entire feature space of the target model to be the same as that of the source model when we naively apply the loss. This may disturb the target model to learn diverse target features that do not exist in the source domain. Even if the target features are learned, the degree of preserved source features cannot be controlled if the source and target features are entangled in the feature space of the target model. Instead of applying the loss to the entire feature space, we introduce an effective strategy, fix noise, that does not disturb target feature learning and allows the different domain features to be disentangled from each other in the feature space of the target model. Our method begins with an assumption that both can be achieved if the source features are mapped in a particular subspace in the feature space of the target model. A final output image is generated from two input components, the latent code, Z, and the per-pixel Gaussian noise, N. If the noise is 0, a feature H' is deterministically generated from a latent code, where H' is a subspace if H corresponding to 0 noise. As shown in the bottom left figure, when each randomly sampled noise is added to small h', it shifts large H' to a space that corresponds to each random noise. This shift of subspace by each noise input consequently expands H' to H. It signifies that the feature space H consists of subspaces corresponding to each random noise. To ensure that the source features are only mapped to a particular subspace of target feature space, we fix the noise input to a single predefined value when the feature matching loss is applied. By substituting noise in feature matching loss to anchor noise, a new loss, Fm', is given. The anchor point gives the model explicit guidance to preserve the source feature in the target feature space. To learn the target features over the entire feature space, we use randomly sampled noise when applying adversarial loss. Our final objective function is the combination of a new feature matching loss and the adversarial loss. We believe that common features of the two domains are embedded in the anchored subspace, and features that exist only in the target are embedded in the remainder space of the target feature space. To sum up, the disentanglement between the different domain features can be achieved in the feature space by the anchor point. The fact that only noise input disentangles the two domain features enables a smooth transition between images by linear interpolation of the anchor point and random noise. The bottom figures shows the smooth transition between different domain features using the noise interpolation. Next, we present several experiments that we conducted. First, we compare our approach with unconditional GANs-based methods. The main drawbacks of previous methods is that they require new models by swapping layers or training to control the source features, which is not suitable for practical application. This consequently affects generation quality. As shown in the figure, previous methods show inconsistent transition and unnatural color transition. In contrast, our method generates the most realistic results and shows smooth transition of different domain features just by using a single model. For quantitative comparison, our approach outperforms the previous methods in all metrics. To be specific, the perceptual smoothness, which is noted as PS, of our method notably outperforms the competing methods, which implies that our approach is more precise and consistent in controlling features across domains. Moreover, when alpha is 0, our method achieved the highest FID in KID. Compared to style GAN2ADA, which does not have any constraints on source preservation, our method shows similar performance while the other methods show significant performance drops. It indicates that, in contrast to previous methods, our proposed method hardly interferes with the learning of the target distribution. We also compare our approach with existing domain translation methods by combining ours with the inversion methods. Compared to the competing methods, our approach generates the most realistic and well-adapted images while preserving the source features. In addition to visual quality, the most notable property of our approach compared to previous methods is that the preserved source features can be controlled in only a single model. This is the end of our presentation. Thank you for listening.